It's called Matter and Measurement, and it truly is a topic that all general chemistry classes start with. And here's our overview, and I've taken this exactly from our e-learning module, so that's why the print seems so small, is that I just copy and pasted it from the overview section in Chapter 1. But it reads everything you touch and feel or taste. It's all composed of chemicals. We know that matter is anything that occupies space and contains matter, mass. Its composition and properties is crucial to our appreciation of the world around us. So it just kind of gives you an idea that as an understanding of matter, which is critical to understanding how matter changes from one form to another, which really is the heart of all chemistry, we begin that journey by understanding measurements. To follow a recipe, to pump gasoline, or to figure out drug dosages, it all involves manipulating numbers. So as we look at our first chapter, we'll define chemistry. We'll look at the different phases of matter, all three states of matter, solid, liquids, and gases. So matter can be classified by the state it's in. It can also be classified by its composition. It can be referred to as pure, a mixture, and we can look at elements and compounds. We'll report measurements using the metric system. We'll learn the application of significant figures. We will practice using scientific notation and standard notation. We will use conversion factors to convert from one unit to another. We'll talk about the 3 temperature scales, one of them being Fahrenheit, perhaps you're used to from our English system, but of course the Celsius and Kelvin scale will come out as well. And finally, the last topic we'll refer to as density and specific gravity. The density, of course, there'll be a lab on this for you, and specific gravity is very similar. So we'll look at those in terms of your learning outcomes. And I'd also want to share, since this is our first chapter together, activities and assessments that you'll be really doing for every single module we cover. You're going to, number 1, complete your lecture guide, and that should be out in front of you right now. As we get started here, you're going to be filling that in as I present the lessons. So you're responsible for printing all of the attached lecture guides, and those are found in the e-learning modules under each chapter. You will then fill in that note pack with all the presented lectures and from your reading. Now, the presented lectures may be in a face-to-face setting, or they may be in an online setting, depending upon your class motto. You'll compile all pages into a single document, one document for submitting, and that's where you use your CAM Scanner app, and you're going to drop that into our assigned Dropbox by the date. And remember, it's your responsibility to make sure you're submitting a correct file. If you submit accidentally 1 page of a 20-page document, it's still considered not accepted. So make sure you check your document when you submit it, that it's the correct document you meant to submit. And then, of course, this goes into your attendance and participation category. So every chapter, you're going to be filling in a note pack with me. And I like to do that because I provide you with example problems and key definitions, and it just allows us to be looking at the same thing together and save you from writing out the examples and gives us more work time on the examples. Every chapter will have a Connect homework site assigned. They are a different number of problems for each chapter, but they all come through as 15 points into your e-learning. And then there is a proctored multiple choice quiz assigned for every chapter as well. And that is a proctored quiz through our remote system called Proctorio, which you're reading about from the introduction module. So chapter 1, the science of everyday experience, known as chemistry. The very first term you're to fill in is the term chemistry. We understand chemistry in itself is the study of matter and its compositions, such as properties and transformations. So when I have a chemical change for existence, one sample of matter changes chemically into another form of matter. Chemistry is the study of matter, so we better understand the term matter. And it's anything that has mass and takes up volume. we will learn and kind of focus in on the last section here that there is a ratio of mass to volume that any composition of matter has, and we'll learn that that's called density. So matter is anything that has density, that ratio of mass and volume. Matter can be naturally occurring substances such as apples. Here's some cotton. This is sand. We have all of these naturally occurring compounds, or it can be a little more interesting in terms of lab development with synthetic materials as well. You can see examples of plastic. I see examples of a medicine called ibuprofen and so forth. So the heart of our journey in this section, in the entire semester really, will be studying matter and the changes it undergoes. I'm going to skip the conversation, just simply let's read it together, and we don't have to say it out loud, but it simply says, what if you're a healthcare professional and you take a blood sample from a patient and you store it in a small container in a refrigerator until it's picked up for analysis in the hospital lab? What might you run into in this ordinary occurrence in a healthcare profession that involves materials, right? That's what chemistry is involved in. You might put on gloves and a mask, use a plastic syringe with a metal needle. You'll store the sample in a test tube or vial. You'll place it in a cold refrigerator. Why don't you think about 5 objects you might encounter during the process and decide if they're made of naturally occurring or synthetic materials. You might want to do this just in your margin. Think about 5 materials, 5 items, and decide if they're natural or synthetic. I'll give you a moment to write them down in your margin. 5 examples. Here are some things you might have placed down. Of course, the naturally occurring matter would have been ice and blood. Synthetic matter might have been those rubber gloves you put on, a mask over your face, the plastic syringe. Even the stainless steel needle is a synthetic material because it's an alloy, a blend of all kinds of different metals. So just getting us thinking about where matter fits into our future profession. What are those types of substances that we'll be encountering in our everyday world that occur from nature and occur from the lab in a synthetic matter? In a next section called the states of matter, this is a section where we review, hopefully it's a review. I'm sure that since middle school or even earlier, you've talked about the 3 phases of matter. And the way that we have, how we compare and contrast the states of matter when thinking at the molecular level. How do the atoms behave in a solid state versus the liquid state, and finally the gaseous state? So this is a section where we just consider the molecular level of the 3 phases of matter. And the first of the 3 phases will be the solid state. The solid state has a definite volume and maintains its shape regardless of its containers. And these particles lie very close together in a very repeated, organized pattern. Solids typically are found as crystalline structures, a very rigid, repeating pattern in 3 dimensions. So notice how closely packed these molecules are. So closely packed that they have hardly any empty space between them at all. Therefore, solids have a definite volume. And it maintains its shape no matter what I do to it. If I place it in a different container. Think of an ice cube. If I take an ice cube and place it into a container, the shape has stayed the same. And we know that's not true for liquids and gases. So just thinking at the molecular level, solid states, very packed together, very organized, and very rigid in their structure. And if you compare that to the organization of the liquid state, a liquid has definite volume. However, it takes the shape of whatever container you put it in. So even though the molecules are close together, they can move past one another. And that vocabulary word is flow. those molecules have the ability to flow past one another, therefore changing shape depending upon its container. But if I transfer, let's say, liquid water from one container into a next, it might change shape depending upon what the shape of the container is, but I haven't added or subtracted in terms of the amount or quantity of that liquid. So liquids can indeed flow past one another. They are less organized than solids, but certainly more organized than gases. And finally, this gaseous state, thinking at the molecular level, we understand that gases have no definite shape. It assumes the shape of whatever container you place it in. It also has no definite volume. So whatever the volume of the container, the gas expands or contracts to make sure that it will occupy the entire area. I just wanted you to know also that gases, they flow past one another as well. They have complete freedom to move about. They have independent motion, not relying on one molecule from the next. Independent motion. Gas particles are very far apart, move very rapidly and randomly. There is no organization to the molecules at all. So we've moved from solids, which are highly organized, to liquids, which are less organized, to the gaseous state, which is just complete chaotic motion. When we think of the states of matter, we begin observing what are known as physical properties. These physical properties I think of as adjectives. What are things we can say about a material that is observed or measured, but does not change the composition of that material? So kind of thinking of adjectives, qualifying descriptors, if you will. What can I say without changing the identity? I can tell you a boiling point. For example, the boiling point of water is 100 degrees Celsius. I'm not telling you anything else but a boiling point, and it isn't changing its identity. I can tell you that water will melt at 0 degrees Celsius. I can refer to solubility. How many grams of salt will dissolve in a certain volume of water? I can tell you a color. Sulfur is yellow. Water is clear typically. I can talk to you about an odor. I can even describe to you the states of matter, if it's gas, liquid, or solid. All of these little adjectives or qualifiers about an object are describing its physical properties. So think of these as just adjectives, qualifying statements that describe a substance. Now on the opposite spectrum of that, the physical change, now we're altering the material. We're not changing its composition, but we're changing the material. So I think of this as a verb. It's an action verb. Whereas the physical property was an adjective, a physical change is a doing word. It's something happening to that object to change its material. We do spend time a little bit later with chemical and physical changes in a future chapter, but just as some common examples, changing phase is an example of a physical property. And what I mean by that is, if I have solid water, we call that ice, and I allow it to melt into liquid water, notice that it still has the same chemical composition. It's still two hydrogens bonded to an oxygen. It just went from a highly organized solid state to a less organized liquid state. And if I have a next phase change by continuing to warm the molecules, I'll go from a liquid state to water vapor, the gaseous state. But notice again, I have the same chemical composition. It's still the same compound. It's just relating to the organization of the molecules. So I represent the physical change. Chemical properties, and again, think of properties as adjectives. Think of chemical change as a verb. Chemical properties determine how a substance can be converted into another substance. So I'm changing its identity. A chemical change is the reaction that occurs. A chemical property describes how the reaction occurs. So remember, if I'm describing, for example, iron has the ability to rust. Iron will rust. Any metal will oxidize over time. I'm describing to you that metals have the chemical property of oxidation. If I actually observe the chemical change, I can write an actual equation to represent the formation of iron oxide, which is what rust is. And again, this is a skill that we'll learn along our journey this semester, is writing out balanced chemical equations. And so if I can represent a change, how I'm taking a pure metal and turning it into a compound, I've oxidized, and that's an example of a chemical change. Notice here, giving us a molecular view of a chemical change, I have a hydrogen molecule here written as H2. I have an oxygen molecule here written as O2. And it looks like I have inside this circle, it looks like I have a total of 4 molecules of hydrogen. And I have 2 molecules of oxygen. And notice how on the product side, these we're learning will be called reactants. On the product side, we've got something completely different. We have water molecules, don't we? We have an oxygen bonded to 2 hydrogens. So that's written as H2O. And do you notice that we have 4 of those all together? So through our journey as we practice, we're going to be talking about chemical change. We just wrote something that's called a reaction. And we express these reactions using this shorthand notation called a chemical equation. We'll learn how to balance those chemical equations and recognize patterns through our journey this semester as well. But at this point, we're just recognizing that we've changed the identity of the initial starting materials known as reactants into something completely different known as water. That is an example of a chemical change. Why don't we practice categorizing if it's a physical or a chemical change? So this is a practice, and I'd encourage you to pause the video, write down a chem or a phys into those lines, and when ready, come back and let's check your work together. Don't cheat yourself now. Stop the video, put an answer, and then come back and check. Okay, you must be ready to check. You've started up the video. It says making ice cubes in letter A. When you make ice cubes, you start with liquid water and turn it into solid water, but it certainly is still water. This is an example of a physical change. We're changing phase, but not identity. And by changing phase, I mean solid, liquid, gas. That's changing the phase, the state of matter. Letter B says I'm burning natural gas, and that of course is going to produce new substances, so that is a chemical change. If I burn natural gas, it releases heat energy, light energy, forming carbon dioxide and water through a process known as combustion. Silver jewelry tarnishing. Well, this is also an example of a chemical change. Pure elements such as silver, and especially metallic elements, as I mentioned iron a moment ago, will oxidize. That's what tarnishing means, is to create a kind of a different substance. It turns pure silver into an oxide of silver. And so that process, just to balance, and it's upsetting some of you, just to balance there, we have a brand new substance formed through an oxidative process called tarnishing. A pile of snow melting, well, again, that's a phase change, just like letter A was. So that's a physical change. And fermenting grapes to make wine. Well, that is a chemical change. Certainly wine has a different chemical composition than grape juice. So a chemical change. How did you do? Did you match ours as we had decided? Great. Here's another one to think about, really kind of wrapping up. It says, does this molecular art represent a chemical change or a physical change? And let's kind of explain our choice. And the heart of this answer kind of lies in looking at the organization of the molecules. And I'm going to call this, and we'll learn that this red molecule represents a diatomic oxygen. And if we don't know that, it doesn't matter. We could just use general letters. Let's call it, let's call the red ones, let's say B. We've got these black atoms in here. I'll call those A. We have some whites. We could call those, how about C? Doesn't matter what we call them. It's just that we recognize that they are different atoms. So I have 2 atoms of this B bonded together. So I'm going to represent that as B sub 2, one molecule of 2 letter B's bonded together. And I have 1, 2, 3, 4 of those. That's what a coefficient represents, is 4 units of a diatomic atom I'm labeling B. What else do we see in this? I called this black mottled atom an A, and I called the white atoms bonded to that as letter C. So that general chemistry there, just generic letters, making them up. For every atom of A, there's 4 atoms of C bonded to it to create a single molecule. And how many do we find in here altogether? I see 2 of them. So now let's see what's happened on the opposite side. It looks like the atoms have now bonded differently. Here is that black mottled atom I called letter A, but bonded to it now are 2 atoms of what I called the red, which was letter B. So I have A bonded to 2 atoms of B, and I'm counting 2 of those over here. And what else? This red atom that we called letter B now has 2 of these white atoms that I called letter C bonded to it. So that compound can be expressed as BC sub 2. And I have 1, 2, 3, 4 of those. Now, to be honest, this is what we have. We have an oxygen, that's the red. This is an oxygen molecule. This represents methane, CH4. Notice the carbon bonded to 4 hydrogens. And so giving you the real substances here. On this side, we see that it formed carbon dioxide and water molecules. So this we recognize as water. This we recognize as carbon dioxide. These are oxygen molecules, and these are what we call methane. So we just kind of decided that we could call them anything we wanted to, but we're learning that they do stand for specific atoms as well. And this truly represents a chemical change because our reactants broke bonds, forming new bonds into brand new substances. So when I break bonds and rearrange them to form new things, that is the definition of a chemical change. And we recognize that CH4 reacted with oxygen, forming water and carbon dioxide. Good. So we've been practicing in terms of recognizing the classification of matter based on its phase. Is it in a solid, liquid, or gas? We then practiced recognizing chemical and physical properties, chemical and physical changes. I'd like to next talk about how we can classify matter based on its composition. What types of matter are in the container? Is it pure? Is it a mixture? Are things being blended? Are they bonded? So in our next section, we're going to talk about the classification of matter. And one of the very first classifications is recognizing if it is either a pure substance or a blend of many things called a mixture. Let's classify and kind of talk deeper about the first of the two choices, called a pure substance. So the first of the two is a pure substance. You're either pure or a mixture. We have to start somewhere, so let's just talk about pure substances first. A pure substance is composed only of a single component. It has really just an atom or a molecule. It has a constant composition regardless of sample size or the origin of the sample. And it cannot be broken down to any other pure substance by ordinary physical changes. Pure substances are one ingredient, right? They're just one thing. Now, if it's pure, it's a single component. It has a constant composition no matter where the sample was taken from, and you cannot break it down further by ordinary physical change. If it's pure, it will either be an atom or a compound. So as we look at examples of pure substances, two examples, here I have table sugar. Table sugar is a compound because it is made of more than one type of atom. In table sugar, I can see a constant composition built 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms, no matter where the source of table sugar, which by the way is called sucrose for its chemical name, it has a constant composition. Here's another example of a compound that is a pure substance, and it's a water molecule. Notice that a water molecule is built of two H's and an O. No matter where it comes from, it has the same chemical composition. So two examples, sugar and water. An element is also considered pure, and it cannot be broken down any further by chemical change. Elements are represented on the periodic table. There's approximately 120 elements on the periodic table. The element are denoted shorthand by using symbols, and we'll practice those coming up. An element is the purest form of matter, right? An element is only one kind of atom. Which was different than a compound. Remember how the compound had two or more different atoms bonded together? A piece of aluminum foil represents the element aluminum with an elemental symbol Al. Here's a tank of nitrogen gas. It's built of an element known as nitrogen, whose elemental symbol is actually N2. It is a diatomic molecule in nature. If I can find matter on the periodic table, I know I can classify it as an element. An element are built of atoms. And an atom, of course, is the basic building block of matter. I cannot break an atom down any further from ordinary chemical means, a basic building block. Whereas compounds, they're also pure because they're bonded together, but they are two or more different kinds of atoms. So if I think about water, it is a chemical compound because I see two different types of atoms in there. I see hydrogens and I see an oxygen. But it's not like I can just physically separate the H's from the O's. They are bonded together. And chemical bonds are not able to just physically separate. And so that's really the key to recognizing a compound, is that all of the different atoms are held together tightly by chemical bonds, creating a single substance. Here's sodium chloride, which is table salt. Sodium chloride is a solid at room temperature. It's very much a rigid three-dimensional crystalline structure. I cannot just go in there and physically pluck out the sodiums and put them in a pile, and physically pluck out the chlorides and put them in a pile. They are chemically bonded together. So NaCl is a single substance because they are bonded together. It is known as a compound. So pure matter, pure is one ingredient. They can be elements built of atoms, or they can be compounds, which are two or more different types of atoms built together. So elements and compounds are both considered pure. Now, if it's not pure, it must be a blend of things. And a blend of things is what we know as a mixture. Mixtures are composed of more than one, two or more components. So a blend of things. When I say blend, it means they are not chemically bonded, but rather just occupying the same container. They have a varying composition, any type of combination of solid, liquid, or gas. Mixtures can be separated into their components by physical change. A blend of two or more ingredients, they have varying composition and can be separated into their components by physical processes. Remember, a compound had a definite composition. A mixture has a varying composition. So let's think of some examples. Sugar dissolved in water is an example of a mixture. It's an example of a homogeneous mixture, a uniform blend throughout. And I can have a concentrated sugar water, or I can have a dilute sugar water. Since its composition can vary, we understand that it's a mixture. And I can separate sugar from water by a physical change. I can evaporate water and get the sugar back, which is another indication that it is a mixture. If it is a homogeneous mixture, it's uniform throughout, like salt water or sugar water, or even a blend of air. Air is a homogeneous mixture. It's composed of nitrogen gas, oxygen gas, carbon dioxide gas, trace amounts of other like helium, and even argon is found in gas. So all kinds of, just a variety of different gaseous molecules, but they're blended uniformly because gases diffuse. So remember, that's one of the characteristics of the gaseous phase. They diffuse to take the shape of the entire container. So it's not like I can walk to one side of the room and have a concentration of oxygen that's greater than in the other side of the room. So homogeneous mixture. Gases will diffuse to take equal distribution throughout the container. Now, examples of heterogeneous mixtures, which means different throughout. Think of a blend of two or more ingredients, but you can see each ingredient separately. For instance, beach sand, Italian salad dressing. I can see each component. So when I think homogeneous, I have just one phase that I can see. Salt water looks the same. If it's pure water or salt water, I can't tell that it's there, as it has one phase. Whereas heterogeneous has two or more phases, things that I see throughout that mixture. So each retaining its own identity I can clearly see different colored speckles of sand. Perhaps if it's beach sand, it might even have crushed shell, pieces of twigs, seaweed, and so forth. So lots of different things there. Let's draw that matter classification flow chart and kind of talk through our definitions. We said chemistry is the study of matter, and so matter is going to go at the top of our classification pyramid. Matter is anything that occupies space and has mass. And as we begin to classify, the first question we ask, does it have a variable or a definite composition? So let's ask a question. We'll say a definite composition. And if that answer is yes, we know that that matter is considered to be pure. And if the answer is no, it must have a variable composition. And therefore we know that now must be a mixture. My pen is writing funny. There we go. So matter, anything that occupies space and has mass. As we begin to classify it based on its composition, to examine what type of matter we have, we ask ourselves, does this matter have a definite composition? No matter where I take it from, is it always the same? If it's yes, it's pure matter. If it's no, it has a variable composition, and therefore it must be a mixture. Let's ask ourselves a next question under pure. Does it have only one kind of atom? If it only has one kind of atom, we labeled that as an element. Running out of room, so I squeezed it in. And if it has more than one kind of atom, we called it a compound. Elements are built of atoms. Elements have symbols on the periodic table. They are the simplest form of matter and cannot be broken down any further. A compound has a chemical formula. In other words, it's built of at least two or more different kinds of atoms, and so we use formulas to tell us how many of each atom there are. An example of a compound could be sodium chloride, could be, we'd had table sugar. An example of elements, we gave aluminum. How about my favorite, gold? We could have the elemental form of sodium, lots to choose from there. Let's come back over here to the mixture and ask ourselves a question, is it a single phase? How many things do you see in that mixture? If it is a single phase, whoops, I should have put yes and no. If it is a single phase, we've made ourselves a homogeneous mixture. Salt water is an example. Let me write that in. We said air is another example. And if it has more than one phase, we called it heterogeneous. More than one phase, we gave an example such as beach sand. That didn't come out very neat. And actually, another good example of heterogeneous would be blood. At the microscopic level, blood is composed of liquid plasma with suspended solids such as red blood cells, white blood cells, and platelets. So it is a heterogeneous mixture. So we've been doing great work practicing how to classify matter based on its composition. And this is the flow chart, very similar to what we drew together. And I kind of went through that with you. So that's kind of the one from your text. Let's practice. What do you see? Is this molecular art an example of an element or a compound? Write down your answer. What do you think? I notice in the first, I have just one kind of atom. One kind of atom we know to be an element. And in this molecular art picture, I have two different kinds of atoms. Therefore, it is a compound, two or more different types of atoms chemically bonded together. What do you think about this picture? Is it pure or is it a mixture? Well, notice in the first picture, we have the identical compound, which is actually a water molecule. Only one type of matter. And so in this circle, we know that that is pure because it contains just the same compound. But over in this picture, I notice I have a molecule of, I'm going to call it O2, two red atoms bonded together. And I have two molecules of CO2, two red and one black atoms bonded together. Since it is two different types of matter, we call that a mixture. Notice they're not bonded together, they're blended together, giving us a mixture. Did you get those? Compound and a mixture. Which representations of the art below here illustrate pure elements, a mixture, a compound, an element, and which is a mixture of two compounds? Well, let's kind of break this apart. Here I have three identical blue atoms, which I know those to be an element, just one kind of atom. And here I see a blue atom and a green atom bonded together. So this is a compound, and I have three of those. So this particular molecular art is a mixture, and I see an element, and I see a compound in that mixture. Blending together in the same container, I see element and a compound. In our next molecular art, these are all identical. They're all white atoms. There's nothing different. So it's a pure substance called an element. Only one type of atom, nothing bonded to it, so it's an element. This might be tricky too. Look at this. It's all the same thing. So it is pure. It's not a blend of things, but there's only one type of atom. So this is a pure element. Some elements, such as oxygen, hydrogen, they exist in nature as diatomic molecules, but since the atoms are still the same, it's still considered an element, one kind of atom. And the last one, I can see that I have a variety of compounds. I have a red atom bonded to a green atom, and I have a blue bonded to a green. These are both compounds, so I can see that it is a mixture, blending two or more ingredients together, and I have two different compounds that are blended together. And so when we compare that we had a mixture of an element and compound. B and C were both elements, and we decided letter D was the mixture of compounds based on the composition there. A few more to practice before we stop here. Classify each as a pure substance or a mixture. Classify each as an element or a compound. I'm going to encourage you to pause. Make sure that you give yourself practice, and then let's check them when you're ready. Come back and let's check together. Okay, welcome back. Let's give it a check. Blood, we recognized as a mixture. As a matter of fact, it is a heterogeneous mixture since it is composed of a variety of different substances. We said it has liquid plasma, and kind of suspended with it is red blood cells, white blood cells, platelets, and so forth. Ocean water, again, this is a mixture. And I guess it would depend on what came up in the ocean water, but I could think of it as a homogeneous solution if it's just salt water. But if I pick up other contaminants and it looks more turbid, it might be heterogeneous. So that's kind of one that is an if. It can go either way. A piece of wood is heterogeneous. I can see that, different composition throughout, especially if it has bark and the wood pulp and so forth. And a chunk of ice really is just, I would say, solid water. So that is a pure substance. It is a compound. The gas inside of a helium balloon, helium is an element. It has an elemental symbol, He. Table sugar is a compound. We're learning it's called sucrose, C12H22O11. The rust on a nail is a compound, again discussed. It has a chemical formula, Fe2O3. An aspirin is also a compound. It is composed of a variety of different elements, carbons, hydrogens, and oxygens to be specific. So you can see up above, we classified blood as hetero, ocean water homo, piece of wood hetero, all mixtures, and the only pure substance was the compound, a solid piece of ice. And in the second, we categorized helium as an element, table sugar as a compound, iron nail that's been rusted is also a compound, as is aspirin, all different elements bonded together. You've done such good work in this first lesson. I'm proud of you. When you're ready to pick up with the second lesson, we'll pick up with metric system in the unit called measurement. I look forward to having you back soon.